We are starting chapter 23 right now, and I'm really excited about starting chapter 23 in part because it's our last chapter, and then also because it's quite a bit easier than everything that we've done this quarter. So if you've made it this far, everything is going to be easier for the rest of the way. So that's a pretty big milestone. Chapter 23 is on amines, and we are going to start, like usual, by talking about some of the basic properties of amines. One thing that is different about this chapter is that we will not learn how to name amines. So you guys have finished nomenclature. You're totally done. The first thing that we're going to talk about with regards to amines are the different types of structures and the way that we classify different structures of amines. We have 5 different types of amines. So first of all, and this one is kind of boring, the nitrogen that has just 3 hydrogens on it and a lone pair. This is a molecule, as you, I'm sure, remember from Gen Chem. This molecule is named ammonia. We are, for the amines, we are definitely able to put alkyl groups on the nitrogen in place of any one of the hydrogens. So what I just drew there is a nitrogen with 1 carbon chain, the R group, and 2 hydrogens. This type of amine we would call a primary amine, just like we have primary alcohols, primary carbocations, primary whatever. Primary indicating that we have just 1 nitrogen-carbon bond in the molecule. And then, of course, as you can imagine, we can put 2 or 3 R groups on that nitrogen. Secondary amine is going to have 2 nitrogen-carbon bonds, and they don't necessarily have to be 2 single bonds. So this would also be a secondary amine. Sometimes it's easier to classify primary, secondary, tertiary based on how many hydrogen atoms there are on the nitrogen. So 3 nitrogen-carbon bonds with no hydrogens at all, we would call that a tertiary amine. And again, that could be like double bond with a single bond or whatever. And then last but not least, we can get 4 alkyl groups on a nitrogen. When we do that, when we have 4 bonds to the nitrogen, it is positively charged. It's a cation. And we call this a quaternary. So we've never seen that before. Quaternary. And it's not an amine anymore because it's got that positive charge on it. It's a quaternary ammonium. Ammonium, not ammonia. Remember, ammonium from Gen Chem is the NH4 plus ion. So this is just a derivative of the ammonium ion. Sometimes these are called quaternary ammonium salts because they have to have some sort of anion to go along with them, like a chloride ion. And salt is our generic word for ionic compound. So next thing we're going to talk about is the geometry or the shape of amines. We're not going to be talking about ammoniums for a while again. The nitrogen in an amine is usually sp3 hybrid. So it's not always the case. For example, up here, this is a nitrogen that's not sp3 hybrid. But typically for most of our amines, the nitrogen is usually sp3. It's got that 1 lone pair plus 3 single bonds. And because it's sp3, we have the potential, in theory, for having R and S in enantiomers. R and S in enantiomers are theoretically possible. We've never even considered applying stereochemistry like R or S to anything other than a carbon. But take a look at this. So here would be, I'm going to try to draw this 3-dimensionally, a nitrogen that has 3 different substituents on it and that lone pair. And so if we knew how to rank the lone pair compared to the hydrogen, the ethyl, and the methyl, we could definitely come up with an R or S ranking for this particular compound. And there is, in fact, a way to rank lone pairs compared to atoms. However, the nitrogen, the lone pair on the nitrogen is in an unhybridized sp orbital, and that lone pair of electrons is free to move from one lobe to the other in that orbital. It can do it at any time, and it does it all the time. So when the lone pair of electrons moves from, I'm going to redraw the orbitals first. When the lone pair of electrons moves from that top lobe down to the bottom lobe, this causes the substituents that are on the nitrogen to be inverted, exactly the same way we would see inversion in an sp or a SN2 reaction. So the stereochemistry just flips as the nitrogen moves, and it's moving back and forth constantly. Those electrons are just flip-flopping from one lobe to the other, which means the substituents are flipping up and down constantly. And because of that, the different enantiomers cannot be isolated or purified or separated from each other. Enantiomers cannot be isolated because we can't get that lone pair of electrons to stop moving. And so anytime you have an amine, it's if enantiomers are theoretically possible, it's always going to be a mixture of the R and the S all the time. And it's not even like a racemic mixture, like 50% R and 50% S, because the R's are turning into S's and the S's are turning into R's. So trying to classify enantiomers is just not useful. So the enantiomers can't be isolated, classification not useful, because it's not permanent. We might say this is an R enantiomer, but in half of a second it's going to become an S, so it's just not even useful to talk about it. So there's that, and that's kind of nice. We'll never have to classify R versus S. The next thing that I want to talk about is solubility of amines in water. Typically, not always, but typically if your amine has 5 carbons or less, it will be soluble in water. And we've talked about this, the problems with making generic rules about solubility, especially with the alcohols, making general rules like if it has a certain number of carbons, it will never be soluble in water. If it has less than those number of carbons, it'll always be soluble in water. There's more to solubility than just how many carbons are there. There's other substituents that might be present, like the halogens or something. Branching makes a difference as well. So this 5 carbon is just a rule of thumb. So we're just going to say usually, and we also have the word typically. And if you're looking at other resources or listening to Khan Academy, this 5 carbon number might be different from one textbook to another, from one resource to another. So remember, just, don't put a whole lot of stock in that number 5. If you're way above 5, it's definitely not going to be soluble in water. And if you're way below, you can't really get that far below, but if you're way below 5, it's going to be soluble in water. And if you're hovering around the 5 area, you gotta, look it up or try to make a prediction based on what other substituents might be on the molecule. And the last thing that we're going to talk about in this video, but not in this section, is the boiling point of amines. Relative boiling points for primary, secondary, and tertiary amines. Primary and secondary amines are able to hydrogen bond because they have NH bonds in them. So that means that they have pretty high boiling points. They have high boiling points. And then tertiary amines, because they have no hydrogens, no nitrogen-hydrogen bond, they are not capable of hydrogen bonding. So they have relatively low boiling points. I just saw what I wrote there. Primary and secondary can hydrogen bond, so they have high boiling points. Tertiary can't hydrogen bond, so they have low boiling points. And let's look at a few side by side. We can compare. Remember, when we're comparing boiling points, what predicts boiling points in part is the intermolecular forces, and then also in part is the mass of the molecule overall. So the heavier the molecule is, the higher its boiling point will be. So when we're doing a comparison, it's useful to compare amines that have the same molecular weight. So we know that weight is not a variable here. And then we can just look at the boiling points. For the primary amine, this one is 50 degrees. This secondary amine is 34. And those are both, pretty high. And then that tertiary amine is 3, which is really, really low. Now, the hydrogen bonding in an amine is not as significant as it is in an alcohol. The strength of the hydrogen bond in an amine is weaker than the strength of an alcohol's hydrogen bonding. So NH hydrogen bond is weaker than an OH hydrogen bond. This is because the OH bond is more polar. The NH bond is less polar. The OH bond has a greater difference in electronegativity, and the NH has a smaller difference in electronegativity. So we've got a big difference in electronegativity, not small, but smaller difference in electronegativity, which means that the hydrogen bonding, the attraction in the OH hydrogen bond is quite a bit more significant than what we see for a nitrogen-hydrogen bond. So what we're going to do next is just sort of look at the difference in hydrogen bonding when it's an NH versus an OH. And we're going to compare this to propane. Again, I'm trying to keep the molecular weights pretty similar. So propane versus this primary amine, which has a molecular weight of 45, so it's a little higher, versus ethanol, which has a molecular weight of 46, but they're all pretty much the same. And the propane, because it has no intermolecular forces at all, except for just the London forces, that's got a very low boiling point, just like we would expect. And ethanol, maybe you remember from lab, has a boiling point of 78 degrees C, so it's pretty high. For the amine right here, this is as a primary amine, it has 2 hydrogens, which means that it has more hydrogen bonding capability than the alcohol does. There's 2 NH bonds, and each one of them is capable of hydrogen bonding, but its boiling point is only 17 degrees. So even though this amine can hydrogen bond in 2 different sites, and the alcohol can only hydrogen bond in 1 site, the amine's boiling point is still a lot lower than the alcohol's. And that, again, is because the nitrogen hydrogen bond is a lot weaker than the oxygen hydrogen bond.